We are now going to derive momentum flux balance, which indirectly is the force balance between two sections, and we will do it for section AB versus CD. So far we have already used Bernoulli equation and hydrostatic pressure condition to derive a few equations like the pressure at point A and pressure at point E. And then we also did mass flux balance to get equation number B, as you see here, that tells us the velocity of ambient above the gravity current. Okay, and now we are going to derive force balance for sections A, B versus CD. A, B and CD. Okay, in the type of forces we have here are pressure force, which basically is hydrostatic pressure that is coming from the density, right? So indirectly that's also the buoyancy force. Okay, and then we have inertia force that represents the momentum term, and we neglect the viscous force. Okay, so we are assuming that flow is in the high Reynolds number regime such that viscous effects are negligible. Okay, and that is why we consider slip condition. So you might have heard of no slip condition. That tells you that the velocity of the fluid at the surface, solid surface, is zero because of no slip condition. But in this case we are not considering viscous effects, and that's why we will consider slip condition. That means there is velocity at all points, and that is why here we are going to balance the pressure force, which actually is also equivalent to, here it's equivalent to the buoyancy force, you can say. Okay, and then the inertia force. So how do we write it? So between A to B we will have P plus rho u square integral of dz, and same thing between C and D, P plus rho square dz. Okay, where this term represents the pressure force and this term represents the momentum, which is also representing the inertia force here. Okay, and why we use rho u square? Because rho u dz, which is actually equal to mass flux. Okay, and if you multiply that with velocity, that gives you momentum flux, right? So you are multiplying m dot with velocity to get your momentum flux. Okay, so we are going to balance pressure. So because fluid hydrostatic fluid, so fluid at rest, Okay, we are considering fluid in motion, considering hydrostatic pressure. So that pressure will be applied in horizontal direction, because pressure applies uniformly in all direction. So we have this horizontal pressure coming because of the pressure from both sides. At the same time, there is velocity in the fluid that creates inertia force. So the forces from A to B must be balanced by forces between C to D. Okay, because there is no other forces. So what we do here is we go from 0 to h, so that is between 0 to between A to B, and we define pressure as Pa minus rho A gz plus rho A u square dz. So what you see here is pressure at any point z. So this is at any point z, where z is measured from the bottom. Okay, we are measuring z from the bottom. Okay, likewise in the right hand side, we go from first 0 to h naught, where we have Pc minus rho naught gz plus rho naught u naught square dz plus h naught to capital H Pe minus rho A g z minus h naught plus rho A ua square. Okay, so these are the pressure conditions we are considering at different points, and also the velocity. So these are different, this will be the expansion of this equation for this particular condition, where in the left hand side we are going from A to B, and considering z at any point we can define pressure. Likewise for the right hand side, we go first from C to E, and then we have pressure condition at any point in between, and then from E to D another pressure condition at any point. Okay, so here we will recall few things. First is that we consider Pc to be 0, that is our reference pressure. So if you go back to the one of, so here we consider Pc to be 0, right? Likewise we have also got what is Pe, and other thing we know is that ua here is u naught is equal to 0, and that is why Pc is equal to 0, and also u naught is equal to 0. That is the gravity current velocity, right? And that is why this becomes 0, this becomes 0. Okay, and Pe is known, Pe is coming from here, that is already defined, and ua is also known. So we are going to use all these equations now. Pa is known, ua is known. So let's replace all these terms one by one. All right, so let's start with the first term here. 0 to h, Pa is known, and that is equal to minus u square rho a by 2, rho a u square by 2 minus rho a gz plus rho a u square dz is equal to 0 to h naught minus rho naught gz dz plus h naught to capital H. PE is again known to us, that is minus rho naught GH naught minus rho naught GH naught minus rho A G Z minus H naught plus rho A UA square. UA square is known, but we will only use it in the end. We will not really replace it for now because UA does not really have either the density term or the velocity, small velocity term, because capital U and capital H are constant, so we are not really bothered about them at the moment. All right, so here these two terms are similar, so we can reduce that to one single term and then we will integrate it further. So this actually becomes rho A U square by 2 Z 0 to h minus rho A G Z square by 2 0 to h, where remember these two things together are giving this term, and that is why we just have one term here, not two terms. Right, and here we get minus rho naught G Z square by 2, that goes from 0 to h naught, and then we have rho naught G h naught Z, that again goes from h naught to capital H, and then we have minus rho A G Z square by 2, that goes from h naught to capital H plus rho A G h naught Z, that goes from h naught to capital H plus rho A UA square Z, that goes from h naught to capital H. Okay, so this is a very straightforward integral which we have got, and now we are going to put the value of capital H in 0 one by one on all these terms. So the first term becomes rho A U square capital H by 2 minus rho A G capital H square by 2 is equal to minus rho naught G H naught square by 2 minus rho naught G H naught capital H minus H naught minus rho A G H square minus H naught square by 2 plus rho A G H naught capital H minus H naught plus rho A UA square H minus H naught. Okay, so these are all the terms we have got. Again, it's just straightforward, nothing tricky about them. And one thing, now you will see that there are few terms which are common and we can get rid of them. So for instance, this red one is same as this one, so this and this cancels out, and all right, and also this one is similar to this one, not exactly the same but similar, so we are going to simplify these two equations accordingly. U square H by 2 is equal to minus G H naught square by 2 rho naught minus rho A. So this particular term is coming from these two things together. All right, and then we have minus G H naught capital H minus H naught this can be written as rho naught minus rho A. So these two things together have formed this particular term here. Okay, this blue one. Okay, and finally we have the last one, that is rho A, UA square H minus H naught. Okay, so what we will do now, we will divide both sides by rho A, and that will give us U square H by 2 minus G H naught by 2 rho naught minus rho A over rho A minus G H naught capital H minus H naught rho naught minus rho A over rho A. Okay, and rho A in the last one gets cancelled, that becomes UA square H minus H naught. Okay, and now few things we need to note here. We know that UA is equal to this particular term that's coming from B, that is mass balance, that is UH H minus H naught. UH H minus H naught, that is UA. And also, if you remember, rho naught minus rho A over rho A times G is actually G prime, right? And what is G prime? That is the reduced gravity parameter that we have already defined in the past, and we are not going to discuss it more, but this is how your reduced gravity is given, where rho naught here is the gravity current density and rho is the ambient density. Okay, so if we make all these changes, this equation actually turns into U square H over 2 minus H square by 2 G prime by 2 minus H naught capital H minus H naught G prime plus U square H minus H naught square H minus H naught. So this is the equation we get, where I have also replaced UA with this formula. Okay, so that gives us this equation, and here this term cancels with the denominator and we get this equation. Okay, so now we can bring this G prime term to the left, and this will become H naught square G prime by 2 plus H naught H minus H naught G prime, and that becomes U square H square over H minus H naught minus U square H over 2. Okay, and here we can again further simplify this equation to make it look like H naught by 2 plus H minus H naught. So we have taken H naught G prime outside, and this becomes simplified. Likewise, here we can take U square H or H minus H naught outside. So this becomes H minus H minus H naught over 2. All right. So this can further be simplified. The H naught G prime, this becomes H minus H naught by 2, and this side is H square H minus H minus H naught, and this becomes 2H minus H plus H naught by 2. Okay, so further this becomes h minus h naught over 2 q square h minus h naught, and that becomes h plus h naught over 2, and the factor of 2 cancels on both sides, and finally we get this equation as u square over h naught g prime becomes 2h minus h naught h minus h naught over h plus h naught, that is also multiplied with h here. So this equation we have got is the momentum flux balance which is added with mass flux balance. So let's call it equation number C, that is momentum flux balance. Okay, where we have so this particular equation that you see is actually a dimensionless equation on two sides, where left hand side has no dimension and right hand side also has no dimension, because this is kept only in form of h, whereas the left hand side is kept in form of u square by h naught g prime, and that becomes dimensionless. Okay, so this is the third equation we have got, and after this we are going to derive energy equation.